Welcome to GeoHug. Happy Friday. So I'll put everyone on mute now, but yes, use the chat. Let me know if you've got any questions at all. So I had several requests to get Richard Scott on today. So thank you for giving the people what they want and joining us and taking the time to share your stories. So Richard's a consultant exploration data scientist for Oz Minerals. He's got multiple postgraduate degrees and training in mathematics, computer science, and information management. So thank you so much. I'm really excited to hear from you today. Thanks again.
No problem. Thanks, Jess. As mentioned, I work for Oz Minerals. I'm officially the data scientist, parenthesis, geoscience, for an exact definition. And today, this is why we're here. Mathymetry, if you like. Although there's probably a little bit more rocks than water, that's good enough explanation for the problem. So basically, South Australia, we've got a cover sequence issue trying to find more deposits. Lots of people are working on this, CRCs, groups like SARIG, universities, companies, and anyone else that comes across a large amount of rock between them and minerals they might like to get to. But no one really wants to drill without a target. Well, data scientists probably want you to because they get some nice negative training points out of that, but that's also very expensive. So for a particular example, my company's interested in IOCGs, or iron oxide copper gold. There's two tools they like to use: geophysics, gravity, and magnetics. So in between the yellow lines is the problem. And as it says there, there's different physics for different types of geophysics. How like a magnetic source is different to a gravity source, and neither gives you an exact answer as an infinite number until you put some constraints on it based on geology and particularly the depth. So that's the reason basically we're interested in a depth of basement model. So in that sense, we want to try and make our own so that we can use that with other functions and other models to improve the effectiveness of our targeting, prospectivity, and various other work. That's the simple version. So where to start? If someone else has already done something, that's always a really good starting point, because science is building on other smart people's work. And in particular, SARIG have a depth of basement grid, which you can see there in the top right. Coloured for the Python people, it's red, blue reversed. So blue is deeper and red is shallower. So that's what theirs currently looks like if you turn it into those colours. So can we be confident in this? Not sure. Can we quantify the uncertainty about that one? Not directly. So do we think we can do a bit of a better job? Probably. This answer, so we thought we would try. And if you have a look, the Exploring for the Future Geoscience Australia abstracts from this year, the people down the bottom, Bondo, Wilford et al., have produced a paper where they've started working on the NT Queensland area where the AusAM survey was done. And on the left, you can see an interpolated grid, a model for a depth surface, and on the right is a machine learning version. So you can see that like the difference in resolution or sharpness, if you like, that looks like that's better. So to make one of these, what do we look at? Is start going through everything that you could possibly use or find, particularly other data sets that cover the area that you're interested in looking at, because that makes it less work and quicker if if you've got multiple data sets covering a particular large scale region that you're interested in, and they can all be easily transformed to work together, then that's a good starting point. So going out from there takes a fair bit more work and data wrangling to join a whole lot of things together. So start with what you have. In this case, we do have drilling and outcrop, which do rely on geologists, as like most of this does. Same with the seismic, but then you need a geophysics expert. Airborne EM, there's only a little bit of. It was publicly available, unlike the example seen earlier for the Northern Territory and Queensland, where they got a very large scale survey that they can handily use. And for gravity and magnetic depth to source, but that's inferred, so that's like a best guess, in general sense, and topographical data sets. So there's a starting point of what we've got available. So drilling, potential field geophysics, topography. Remote sensing used, say, for a Cenozoic surface, but not for depths. We don't have statewide MT yet, but hopefully in the not too distant future. So that would be certainly worth trying. And we don't really have a statewide seismic data set in the same way that SARIC's done gravity and magnetics, radiometrics, etc. for us. But in a paper recently released, there were some seismic models for Australia, multiple versions of them. They had some ones covering the globe as well, you can see there, but 5 kilometre scale seismic models for Australia were good enough, I thought, to throw in and give it a try. In the SARIC depth to basement data set, there's lots of information, 380,000 seismic interpreted points, a few thousand magnetic if you pull them out of the recent Gawler-Creighton airborne survey, and 1,000 airborne EM points, 85,000 outcrop polygons, and 26,000 drill holes. So how to go through this? Again, use something that perhaps is like fit for the task and makes things easier to repeat. And here we have Uncover ML, which again is detailed in this year's Exploring for the Future abstracts. It's a machine learning framework that's publicly available on GitHub that anyone can use. And it's specifically designed for working with geoscientists, so Geoscience Australia, people that aren't machine learning or software experts can run models via this framework. And sometimes on the national supercomputer, it's designed to work with that as well for when they want to do really broad scale things, like when they might have weather people or whatever, doing like huge problems that are sort of a bit bigger than we've got to deal with. So basically it takes in raster data sets, runs a model over them, and gives you back a map at the end. It's also a raster. So like good for geoscientists to look at. And it also will give you the same thing, but an uncertainty layer or variance or standard deviation, or however you want to look at it as well, depending on the model you use. So that's a really useful thing to see where you may have data problems or need to get more data, or you just can't believe things as much. So a bit more detail. And again, it's geoscience focused, so it takes input target training data, which is in this case the drill holes. So a shapefile of those, they may have other fields in it as well, but you just need the geometry of the drill hole locations in the same projections as your raster inputs. And it will also produce, the machine learning information, how good the model is, the diagnostics, and it's all in a set format. So it spits you out these files, labeled the same as your input configuration file. So they're there, and if something goes wrong or you have a problem, you can run it again and you get the exact same lot spit out again, and then you just change the name a little bit, you get another version. So it's good for housekeeping and paperwork, I guess, if you like, in that sense, and then keeping track of things rather than having to roll your own or write that yourself. That's quite good. That's quite good there. It's also, unlike something you might write yourself, it's got some quite specific requirements. You have to have everything in the same projection and resolution, so that will require tweaking your inputs a little bit. And again, it's like a work in progress. It's out there in the public, and like most things science, it basically, you know, it's a Unix tool originally. So I had to get on working on Windows 10, so it would work at work. It's a bit more complicated and a bit flakier in general, so that required a bit of like, you know, software development, computer science stuff to get it going. But the majority of the problem is solved for this particular case. No neural network capability as yet. But that didn't matter here because that wasn't what I wanted. So to start with, we have a reasonable degree of overlap in some of our high confidence data sets. So the outcrop area and the drill holes, that area is quite a bit the same for obvious reasons. So whether it's worth using the outcrop is basically saying 80,000 times that there's no depth here and a lot. So, and 26,000 drill holes, 80,000 outcrop points, that makes your training data 4 times as large. So basically things will take 4 times as long to run approximately. So for like a first pass solution, not ideal, because if you do something the first time and it's rubbish, you'd rather spend 40 minutes doing it than 4 hours. This is a basic theory. So in data wrangling, you expect some problems, data type errors, null data, missing geometry, wrong coordinates, you know, your raster data handling. When you work with a new framework, even though it's designed to work well and be fairly straightforward, you've got to get the hang of it, whether, you know, you type in some of the like configuration words wrong, or it's on the wrong line, or that sort of thing. So you get that done. But once you've got one version of it, then you just save as, and you've got the next version and everything else is right, and you just change a particular configuration for the model and you're ready to go for the next one. So once you've got the hang of it, that's good. So obviously to get to this point, you need some level of knowledge of programming, machine learning. So that's a data scientist job to this point. But if you've got someone like that that can set it up for you and you know what models you want to try, all you have to be able to do is like write the configuration file and type uncover ML, learn this configuration file. And that's it, and then come back when it's done. So math, statistics, physics, computer science, all good. Chemistry's good too, in that sense, and it definitely helps if you know something about geology, geophysics. But I only ever did a year of geology, so I was sort of learning some of this stuff as we go. So, the first time, the Geoscience Australia model we saw earlier by Wilfred von Doe and company was a support vector regression. So basically it's spitting you out numbers, as in like the exact depths that it thinks for the basement, as opposed to like classifying where it might say shallow or deep. So I went with the so I did a test run on a few thousand data points to try and get things working. So that would work really quickly, you know, run in just a few minutes. So you get an answer, was it worth putting gravity in? Yes. Was it worth putting magnetics in? Yes. Is it worth trying this? And you get answers back in just a few minutes rather than waiting a few hours. So it's good for like fast iteration of what it's worth trying with more data at a longer scale and more complicated model that's probably got better prediction capabilities. And then mentioned before, 26,000 drill holes. So that was the training data. And basically what a support vector regression is trying to do is divide all your different features in many dimensional space and separate them as well as the algorithm can. That's the simple version. There's a 2-dimensional version of that though. So the support vector is trying to get that maximum distance as possible between dividing the groups. Support vector regression is also slowish, so to run 500,000 points, not really doable without access to supercomputers, which, not being Geoscience Australia, currently do not. In the first version, not too bad. So that's basically the difference. On the left is the SARIG grid that we showed earlier, and that's what the output from that first support vector machine run looked like. So we'll see some more detail, and it doesn't have the sort of hard to interpret optically or looking at it, smearing that interpolated grids can often get. So you have to like zoom in a lot to see what's going on there. It's a bit clearer in the model version there. So it looks similar sort of looking difference to Wilford abstract from before. So that was pleasing. It seemed to be at least on the right track. So what to try next? Earlier in the year, I went to an international conference on machine learning and talked to some people there, some reason for going, and actually got to talk to, I'd seen this like particular type of model mentioned before, like a few months earlier. I actually got to talk to the people about it, say, could we use it for this exact problem? I still didn't want to bother doing it if they didn't think it would be sensible or what they designed it for would be no good. So I said, yeah, probably that should be okay. So I thought, we'll give it a go. So the difference between NGBoost and some other models is it's designed to give you a probability distribution prediction, not just a point where it says, we expect that it'll be 430 meters here. It'll give you the probability that it'll be 430 meters. So like plus or minus, if you put in a normal distribution, you'll get 430 meters will be the mean, and it'll give you the standard deviation. You can plug that into your normal distribution and work out what's the probability that it'll be 600 meters. And if 600 meters you don't want to drill at because it would cost you too much, and if the probability is too high, 600 meters, then you'd skip that one. So good from that point of view. It can use a decision tree as the base part of the model, which is also a useful thing. It's a bit slower because of the gradient boosting calculus part of it. So that's slightly more annoying. And this is separate, so not part of Uncover, and they also have to write your own map producing code to get the output that you want out of it at the end. But luckily, a geoscientist, the programmer, had written a library that does the basics of that for you. You'll take like a stack of rasters put together and do the prediction crunching on them and spit you back at like the prediction raster map at the end. Hack that so that it would spit back two maps for that particular probability distribution. So a little bit of programming there, but not too difficult. So tried that one, and then if those are interesting, then random forests of any particular flavor might be interesting as well. And often in geoscience type problems, if you look in the scientific literature, random forests do get used because one particular strength is they can handle non-linear relationships pretty well. And you can also look at the outputs. You can look at the individual trees, and you see on the diagram below. So you can see where's it split the data at the start, which say, for example, there may be a regolith depth, for example, and then go to the next thing and say, right, gravity here, gravity is higher than this, go there, there. So you can actually trace those through if you want to understand the most important data points as far as the algorithms looking at. So that improved things even more. So that was good. Intuition was correct there. So the NG Boost version there is on the left. Now that is considerably bluer than the one on the right. So that's sort of suggesting that the state is much deeper on average than that model. So do we believe that all of South Australia is like really that deep? Maybe not. Geoscience question. So that is progress in 3 dimensions. So there's the random forest model in a 3D view. So when you see like the 2-dimensional, so you can actually sort of see in a little bit better where the depth variations appear to be, and where it goes up and down more, so it's a little bit easier to look at. And that's the same thing, taking on a little bit of a tour. And again, iterative process. Something else suggested by Geoscience Australia is looking at wavelet, basically wavelet decomposition. So look at higher wavelength features in various things like the gravity or the magnetics, and add those in as well. So you have the base version of the raster, and then double the wavelength version and the quadruple the wavelength version, etc. And put those in and see if that makes things better, because they suggest that lots of these geoscience features or natural features have like a fractal dimension that the higher wavelengths can, longer wavelengths can pull data out of. So that seemed to work to some degree. When I was doing the Neo-Proterozoic trial, from just like a quickly put together data set, going from the base level and putting those in improved it a lot. So I guess it probably varies depending on the use case, but still seems to be a useful technique. And considering even further from there, there's a lot of drill holes that don't get to the basement, but if you've got to 100 meters and you haven't hit it, it's at least 100 meters deep. So some work that the CSIRO or what's now Data 61 did, that you'll find on the Uncover ML page, is look at that particular problem, like on a small scale example. So you basically got a compound likelihood or multiple possibilities where you know that you've hit basement, or you know you've hit a certain depth and haven't, and you try and constrain that with a linear model, like a linear regression type thing. So that in this particular example, that will work for like a small area, but you can't really do a whole state like that too easily, because then if you're familiar with the linear regression model, y equals mx plus b, where b is a constant, and in this case, the constant will be your mean depth. And mean depth for a state, probably not too interesting a piece of information. So I haven't got any further with that part as yet, but would show some promise to use some sort of technique along those lines to fine tune depth predictions, because if you've got some that are deeper or like shallower than that all this drilling's gone to, that's already been done, then obviously they're wrong, and those points are wrong there anyway. So it can be upgraded in that sense. So maybe look at doing that by breaking it down into smaller areas across the state that are reasonably similar, and a technique like the above might work, or you just have to take that mathematics or modeling, that sort of thing further, which requires some reasonable amount of thought, unfortunately. So next question, which one do we believe, or believe the most? Like the original SARIG grid models we've developed, which particular family, some some other model that we haven't tried yet. I did try explainable boosting machine, which is another sort of general linear model. They weren't too bad, but closer to the NG burst variety than the random forest variety. We'll try neural networks do a better job, given you've got a whole lot of image input that you can use. Maybe they will. More complex to do, but might give you a better result. And just there's the two-dimensional version of the standard deviation output. So how variable that models are in general. And as you probably guess, the deeper somewhere is, the bigger your standard deviation is going to be. So and you want a coefficient of variation output, not the standard deviation. So it's more standardized and doesn't vary as much by the actual depth. But you're never going to get much standard deviation of output on, when you know that the basement's right on top. So they can't really vary very much. So it's probably like more helpful for a more middling part of the range. And a human part of the work, you got a whole bunch of decision trees. You need to look at some of them to see what's going on. And does that make sense in a geoscience point of view? So you got to grab a geologist by whatever part you can drag them in and get them to have a look at it for you and see if it makes sense. Or a geophysicist, but there's fewer of those to grab usually. So it requires a bit of collaboration, which is always important. Like multidisciplinary teams generally get better results according to the research. It's something I believe. So, and again, down the bottom, most of the work, doing all the data wrangling, etc., and then do it all again once you decide how you can improve this, more features you want to put in, engineer, change. Do you try a whole bunch of horizontal gradients, or some sort of other derivatives, or some sort of other filters, or other data sets, if you can get them or find them. So an iterative process. If you don't think the one you've got is already good enough, if you think it's good enough for purpose, then you're good to go and can work on something else. But this one probably needs a bit more work and verification, but it's definitely promising. What we do with it, probably a lot, and we actually used it a couple of times recently in evaluating some projects or possible opportunities or ground to go and grab. And other areas you'd feed it into, like target evaluations, drill planning, inversions. We've got an economic modeling stream going at work, so builds into there. Various other surveys and better idea of what the targets might look like in general. And why do we do it at state scale? Because speaking of inversions and everything, we want to look at the whole state. And here's a plug, Drillanthropy, which is a South Australian initiative. So Oz Minerals will fund drill testing of data science supported copper exploration targets next year. So if you've got something there, or some ground with some interesting targets, or some interesting targets you want to find, exist on someone else's, which we can maybe help out with, have a look, get in touch. And know that there's been a lot of good data science type work out there, and the Explorer SA Gawler Challenge recently, I've read all those, so there's definitely some really good work there. So you look at those models, find something interesting on projects you're associated with, then don't care if you're the smallest or biggest company. We're very happy to collaborate on testing some of these ideas so we can do better exploration. Okay, that's that. And this wouldn't have been possible to do as quickly without people listed here: SARI, Geoscience Australia, the Software Underground, people have done all the hard work developing Python geoscience libraries, some of the Explore SA people for an idea or two and conversations. So that's all for the presentation. Thanks very much. Thanks for listening.
Thank you so much for that. Everyone's welcome to jump off mute if you like. If you've got any questions or comments, let us know.
Anyone else working on something similar along these lines? I've seen a Queensland basement domains map come out recently that was interesting. Didn't have a grid with it. Haven't looked at any other states yet, but I'd certainly be interested to know.
We've had one question. Did you extend this at all to other states?
Not yet, but definitely
Plan to?
Something I'm working on. Probably Queensland and the Northern Territory next, I think. If anyone's got like large already classified drill hole databases, feel free to get in touch too, because that certainly can speed up the first iteration if those have all been classified by professionals already into what you call basement and what you don't. So there's a bit of a trick there that's for expert geologists in that sense, as opposed to running like some sort of rules going, all right, this is sandy, so it's not basement. And with Queensland Northern Territory, they have that airborne EM survey. You can use as another input there too, even if Queensland doesn't have their own whole of state geophysics like South Australia does. And that's another layer that can go in there that should be quite useful.
Had another one come through. In the cases that you used in this model, how did it perform?
Only sort of used it two or three times recently, so it hasn't been done for that long. It's like literally 4 weeks old, maybe. So pretty reasonably, I think, so far. But it's like, the first pass, so only very little bit of validation, so to speak, sort of on the fly, without going through all the science of looking at, does this bit make sense? Does this bit make sense, from research or whatever in particular areas on particular formations? And so that piece still needs doing, but it seemed to make sense when we're looking at it at the time. Too new to tell. Has anyone worked a lot with the South Australian cover thickness grid or anything else similar recently or in the past? So I'm always interested in talking to people who are working on things like this. And you never know if inside secret bunkers in companies or houses or whatever, people are doing something similar. So feel free to get in touch.
There's lots of thank yous coming your way, so.
Thanks. And just tried this with the South Australian geophysics data. I didn't try it with the Australian version, and apparently get more new gravity stuff coming out this week. So it'll be interesting to compare results from different areas there.
Hi, this is Rebecca. This might be totally out there, but thought I'd ask. So I know this is looking at more geospatial data sets, but could anything else be applied to it as well, like mineralogy or anything like that? Not yet.
It could be.
Yep.
For states, for the trick would be getting it, having enough of it to be useful for a state scale. Yep,
that's fair.
Yeah, but you could, I guess, drill down if you want to use those words and look at if say you had some other data set that covered whether it was the Gawler Craton or the northeast or something, and you wanted to do the same thing again over that area, even if you use this as a starting point, then you could certainly like do that sort of thing. Like the Gawler Craton Airborne Survey covers that with, you know, nicer magnetics. So that could be done over that area and compare the differences or see if it performs better.
Yeah. All right. Thank you.
Sure. So they might be worth breaking it up like that. And if you're doing big regional chunks, then that's not as too much more work. Ideally, you could automate it all and throw everything in, and
That's right. Yeah.
over whatever like few kilometre area you wanted. That would be the ideal situation, but we have to get to that point yet.
I had one. What's your favourite part of the state to drill for new deposits?
I would say that any that like people's data science workers said looks interesting that people haven't. So somewhere that someone hasn't done it yet. So I'm not sure it'd be like a favourite part in that sense. It would be a new part.
New part.
And someone's got a model that said, this looks really good and it seems to make sense that it's really good and no one's done it. So it'd be hard to say a particular place.
Here we go. Can the same approach be used on projects rather than state if you have large quantities of data?
Definitely. That would, yeah, I think as I was saying before, you can certainly like focus in if you've got more data and more layers and information about the basement and training points in a smaller scale. Absolutely. Sort of, I suppose, like exploration's a multi-scale problem from country to state to region to area to project, as you mentioned there. So it's definitely repeatable all the way down until you get to too little area that it mightn't be worth the work almost. So that's certainly worth trying. So would like to try, you know, say like there's some MT surveys in bits of Queensland. So it'd be interesting to try it in an area where those cover. So you could use that layer there. Is that certainly like something that, you know, looks deep underground in that sense? It'd be quite interesting, you know, down to the lake depth that we're talking about. And then that may give you some indication which layers may be useful if they're completed on a broader scale, or, you know, okay, that seemed to make that a fair bit better. So we've got MT for X percentage of South Australia, so we should do that bit because the model for that part where we've got it will be this much better. So it's like worth trying from a verification of how you can improve the other model.
Another one, you mentioned Uncover ML doesn't do deep learning. Would applying a neural network to this problem give a better result?
Possibly. Because like convolutional neural networks, particularly good at dealing with images, and if filters of some sort of improve things, the neural network, like working out convolutions and its own feature layers that are filters as such, it may come up with, you know, as part of the modeling process, features and filters that are particularly useful that you would have never thought of, like in non-linear combinations of such. So it may improve things because of that capability. It'd probably be like more that it does something different from that point of view as to why it would work better, but it requires, so like machine learning, I guess data science, you got a computing trade-off, like how long will it take, how much will it cost, and how complicated it is. Whereas neural networks, like the most complicated machine learning models to run, because you've got to like set them up, use frameworks to get them to run in a reasonable amount of time. You've got to have generally speaking, an NVIDIA GPU. Maybe some models like this could run on a smaller scale. If you have smaller scale ones, it'll fit in, you know, like something that like a laptop sized GPU, then that's fine. But when you're starting to get bigger than that, it can be pretty expensive, and you start renting cloud computers that can cost several dollars an hour to run. And if you've got a model that's going to run for a day or two, you know, it adds up fairly quickly. So is it better enough that it's worth spending that much money on, in that sense? Like in a continent, so like Australia's a fairly big place, so running a continent-wide model take quite a bit of RAM and fit all your raster layers for across the country in. You need a big enough GPU to fit in, which is not likely to be a laptop unless you're reducing the resolution. Another thing we did with this trial is ran it at 1,000 meter resolution, so it would run fast enough and be able to run on, like, you know, your own workstation. So you can do trials there without costing too much money. Because if you're running it on, you know, $100 a day extra or whatever on a cloud computer while you're doing stuff and you're not quite sure you know what you're doing, it's probably not worth the money. So, but narrow it down to say like 400 meters or 300 or 200 that a exploration geologist doing drill targeting would want. It'll take several times longer to run, cost more, so you want to be sure of the particular model that you want to run before you do that, unless no one cares about the budget. And if someone just comes and says, do whatever you want, that's fine, but you generally got financial constraints on whatever most people do on what they're doing, unless they're, you know, tinkering on their own. So there's another problem there. So we need to try this at high resolution, see how it does there. Better, worse, worth the time and money.
Why is variance in random forests raise the degree of uncertainty?
I'm not sure. Well, the uncertainty is the same. The uncertainty about what you're doing in a professional sense is sort of the same, but random forests, each tree that you run is got a degree of randomness, so there'll be a slightly different result for each tree. So you put those together, you get a variance number. If you're like, one says 100 and another one says 101, another one says 133, and another one says 135, and one says 200, and one says 50, then you get a standard deviation number out of that. But usually, like, the more trees you have, you know, the smaller that will get. But the more trees that you put into your random forest, the longer it takes to run. So, but it can give you a measure of that uncertainty, instead of like how big or small it might be in a particular point. Because like every 1,000 kilometers square is going to have a different number, and bigger or smaller variance based on, you know, the magnitude of the depth. Like if you're out 10% at a 2,000 meter depth estimation, you're 200 meters out. If you're out 10% at 15 meters, it's 1.5 meters. So it's a bigger number, but, you know, relatively the same uncertainty in that sense.
Did anyone else have anything? You're welcome. Yeah, welcome to turn your cameras on, turn your mics on, have a chat.
clever ideas, let us know. Anyone's a
Yeah.
seismic guru, interested in what we can do with that, like in a more sophisticated manner too. Need to like on Software Underground, there's quite a few people from the energy industry in the Northern Hemisphere, so need to pick their brains about what we can do with this seismic data that's like lying around Australia, and it's probably a bit underutilized by mining people in that sense. But again, doesn't cover the whole area. We've got lines here and lines there. So what do we do with that part as far as, trialing in certain areas?
Hey, Richard, well done. Good talk. Thanks very much.
Yeah, it was great.
Same goes with like thermal things, like geothermal people, got any clever ideas? Don't know much about that. So heat things.
Pretty much anything.
Yeah, anything anyone thinks might work. It's like,
Yeah.
if you've got a framework, you can throw it into easily and consistently and just sort of hit run and then compare the results to your last batch that's in a nicely organized folder. It's good.
Yeah, you never know what might drop out the other end.
Yeah, that's right. So like, and if you're doing trials that are like low cost and reasonably quick, and sort of like, and turn them on and come back and look after lunch, it's not really any big deal, and it's not like eating up all your CPU processing power if you're trying to do something else. It's a fine use of resources there. Scale it up later.
But thank you so much for your time today. Really appreciate you coming on and talking to us.
No problem. Thanks for having me, Jessica.
Thank you everyone for joining, and hopefully see you again next time.